I work in probabilistic machine learning broadly. I work with Professor Justin Monte and Professor Daniel Sheldon right now. Um, the talk that I'll be presenting today will talk about probabilistic inference in probabilistic models. One of the things that we have recently done has been published in NeurIPS. NeurIPS is one of the big, or probably the biggest conference in machine learning. We'll be presenting this paper in like 15 days from now. So we'll be talking about some really cutting edge stuff very soon.
I'll let you know that it is a big conference. It was big enough that I got rejected from it, so congrats. No, it's an important conference. I've always heard that Domke's lab puts a lot of papers in there too, so you guys do good work. All right, I'll open the floor to you now.
Interestingly, has had a very strange relationship with NeurIPS. Like he only publishes to NeurIPS, and he publishes a lot to NeurIPS.
He does. Yeah. If anyone has any questions about that, yeah. Sorry, I was going to ask if anyone has any questions about that stuff real quick, like your lab or anything like that, I would let them ask now, and then we can get into actual content. I give them like a second to do that, but then I'll turn it over to you completely. All right, yeah, okay, well, let's get into it. All right, I'll mute now.
Okay, yeah, hi guys. So we'll be talking about this. So I'll be dividing this talk into two phases. The phase one will introduce what is variational inference. Think of variational inference right now as a concept, a solution to a very, very general problem. Then we'll talk about a subclass of those solutions, a smaller domain of solutions. And then we'll talk about how to automate that subdomain of solutions. So that will be the overall idea in phase one that will familiarize you guys with the concepts involved. And in phase two, we will go after some of the very recent deep learning based advances that have come up. These have been very relevant to the broader class variational inference, but they have not been evaluated in the subdomain that we'll talk about again. Because of that, we were unaware if those new advances could automate or better automate or improve this subdomain of solutions. So that's the broader idea of the overall talk. That's what you should be able to take away. In the meantime, I'll take questions as we go. So if there is anything that's bugging you, you can just go ahead and ask that and stop me. So let's go with the phase one. So as I said, variational inference is a solution or class of solutions. And before we get to that solution, we need to understand the problem. So the problem that we consider over here is not a very specific problem. In case it's actually a very general problem. So an expert can create a model PZ, X. And what this means is that Z is the collection of the latent variables or the hidden things, and X is the collection of the things that will be observed. To use an exemplar model, I came up with one that all of us have, at least all the humans have, is the model of human face images. So all of us are very, very advanced and experts in this model. We're given a human face image, we can evaluate it, and we know that, okay, this is actually a human face image, at least close to it. However, even though all of us have this model, you can be presented with data which has some part of it missing and some part of it that is observed. So over here we have this image where the first half is sort of missing and hidden to us, and only the lower half of the face is available. So with this, if I gave you options A and B, all of us are somehow able to evaluate option A and option B and say that option A is less likely the missing part as compared to option B, which is probably more likely. Even though we know that option B is probably not the answer, we somehow know that it's more likely than option A. Also, we know that option B is not likely the actual answer, the true answer, because we're somehow using the observed information pretty well. And if you want to summarize that, what we are doing is we are using this quantity, which is PZ given X, which is probability distribution over Z, the missing part, given the information that I already have. And this is the quantity that is known as the posterior distribution and is the main quantity of interest in any probabilistic setting or in any probabilistic model. So we'll be talking about this, we'll be approximating this, and we'll be going after this. However, we cannot evaluate this quantity just given the model. So remember, we talked about that the expert will only give us the model PZ given X, the joint distribution. And that's the only thing that we have. If you wanted to evaluate the posterior distribution, we would want to do something like this, which comes from Bayes' rule, which is very fundamental to probability. Bayes' rule says exactly this, that if you want to evaluate conditional distributions, which is PZ given X, you will have to do it in this way, where the numerator has the joint distribution, and the denominator has the distribution, the marginal distribution of the observed quantity. This is just the definition of Bayes' rule. However, as we said earlier, that the only thing that the expert sort of defines or wants to define is the joint distribution. What I want to emphasize is that we do not have the denominator. To be able to evaluate denominator, we have to do something like this because we only have the access to the joint distribution. And this tells you that why we cannot evaluate the conditional distribution, the posterior. The denominator involves an integral, which means that you will have to integrate out the variable z, and then only you will be able to evaluate it for one instance. Sorry, Cooper, am I doing fine?
Oh, yeah.
I'm getting a lot of...
Yeah, here.
Right.
Yep, no, it's all working right.
Cool. Yeah, so this should probably give you some idea of why it's not possible to evaluate it. This integration is in general very hard. Integration is the reason why we cannot do a lot of simulations. A lot of physics doesn't work. A lot of what we do cannot work because integration is hard. We do not know this integral in closed form, nor we can numerically calculate it exactly. So that's why evaluating the posterior is hard. And also we do not know how to sample from it. So probably you would have wanted to do something like this. Given the data, given the lower half of the image, you would have wanted to sample from this distribution. And if you probably sample from distribution, you would have ended up with something that looks like this, which is very, very close to the real image. But we cannot do that. Why we cannot do that is as simple as not being able to evaluate it. We do not know the form of EZ2X. To even evaluate it, we need a lot of computation. And even if we are able to evaluate it, we do not know a mechanism of how to sample from it. Knowing a distribution and being able to sample from it are two very different things. You know what a Gaussian distribution looks like, but being able to sample from it is an entirely different story. So for this reason, we do what all good computer scientists do. We approximate the distribution that we are interested in. This is where different methods will come in. There are MCMC techniques, there are variational inference, and some other techniques to approximate this quantity of interest. We'll be focusing on one of them, which is variational inference. If anyone has any questions at this point, we'd like to take this up. This is sort of about why you want to care about this thing.
I think it might be worth going over how we think of the model as a distribution. I think that might confuse a couple people. I'm not sure, though, how well people do with statistics.
Oh, sure. I actually wanted to remove that from the discussion because it's often hard to think of it as a specific distribution that you start with. So I thought of trying to get away from that discussion, but if people are really concerned about that, I can go into that.
Yeah, I think hopefully people are on board with everything else.
Okay, good. Sure. So sure. So right. So the aim till now is that we want to approximate, or we want to care about this posterior, and we want to approximate it with something. And the thing that we will approximate it, we will start calling that Q. So Q is the distribution that we want to approximate the posterior with. And before we get into how we do that, we have to look at a derivation that is sort of something that we cannot get away with. So over here, I have an equation written, which should probably be intuitive. It could be that it's not for some people. What I have written over here is that log px is equal to the expectation taken over this distribution Q of log px. Now, this equality holds because the distribution that we are taking the expectation over is with respect to z with respect to q. It's a distribution q with respect to z. And the quantity is px, which is independent of anything a z has to say. Essentially, log px is a constant. That's why the equality holds. However, you can play around with this equation. And if you play around with this equation by multiplying and dividing it with the same quantity twice, you end up with something that looks like this. So over here, what we have is that these are just multiplication and division by the same quantity. And we are just combining px with pz comma x, something which is the definition of the posterior that we saw just on the last slide. Once you do that, it sort of appears why you do this. You can divide this quantity log px into two things that will be very essential to the entire discussion of variational inference. We call the first thing elbow, and we call the second thing KL divergence. Why do we call it elbow? It's not the actual elbow, it's evidence lower bound. What we call as evidence is x, the thing that was observed, and log px, which is the log probability of observing the thing, as the evidence that we have. Elbow, the quantity over here, is lower bounding the evidence, and hence its name, evidence lower bound. And the reason it lower bounds is because of this term KL, which is a close to a distance metric. It calculates or approximates the distance between two distributions. In this case, it being the distribution Q that we want as our approximation and the true posterior that we were interested in. Since a distance metric can be only positive, the scale term is only greater than equal to 0. I do want to emphasize that it's not exactly a distance metric, but it behaves very, very similar to that. So having established that log px, the evidence can be broken down into these two quantities, we want to focus on the KL term, which we said that is a distance metric. We want to minimize this distance, and if we have the minimum of this distance, we'll have a Q that is very, very close, or at least as close as it can be, to the posterior that we were interested in. Now, the trick here is that the expression for this KL divergence looks like this, which involves evaluating PZ given X. And we just discussed that evaluating PZ given X is not possible. It's just computationally too expensive for us. So as a hack, what we do is that we look at the KL divergence in another way, where we replace it by log px, subtract the elbow term from it. If you take a look at the equation above, which is the equality, we can always do that. Once we take a look at this, we somehow see that this minimization problem is equivalent to another maximization problem. And the reason for that is what we discussed briefly earlier, that log px is constant with respect to q or z. So it has nothing to do with z, and so this can be ignored, and then the negative can be transformed into a maximization problem. Once we have this, if you look at this expression, this is a more familiar expression, and this is a more amenable expression in the sense that we can evaluate this if q is well behaved, and we know all the quantities that are involved in this, and probably we can maximize this also. However, the question remains that how are you going to maximize through? What's happening over here is that we are searching for Q, we are searching for different Qs that we're going to minimize our tail level. But what we were searching for is searching within a family, searching within Gaussian distributions. When we were searching within a family, we were evaluating different members of that family, and the Q that gives us the minimal tail divergence, we were going to say that use this Q, this is our approximation. Now, to search through a family is a very hard thing. Think of the family as a Gaussian distribution with variance fixed to 1. The only thing that you have to change is the mean. Now, the mean can be 0, 2, 3, 4, or any other number. Instead of evaluating all those numbers, we want to be smart about it. And the way to be smart about it is that we parameterize the family. When we say that we parameterize the family, what we do is that we say that mean is mu, and then I'm going to optimize this objective with respect to mu. And whatever value that I'll end up for mu, I'll say that this is the parameters, these are the parameters for that best possible approximation. And this is what we do. This is the basic idea of VI. You have a parameterized family. You search through that parameterized family by optimization such that you can approximate the posterior. So the idea is that you use gradient-based optimizations because we can run them on GPUs and do amazing things with them. So you have this objective that you're going to maximize using the gradient-based method, and you should be done. The question is, are we done? And we'll get to how the story gets more complicated. Are there any questions at this point that probably we can take up?
I'm gonna go ahead and guess that lost a couple people. It's a little math heavy. I think it might be worth doing like a recap of sort of the idea of what we're doing. Like this idea that we are trying to approximate the conditional probability and all of that. I think maybe got lost along the way for some people. If you want to try just recapping.
No, sure. It is just a mathematically heavy thing. But yeah, so the general idea of VI is that we want to approximate this posterior that we talked about earlier. However, there aren't any easy ways to do this. There is a mathematically elegant way to do this, which is sort of we discussed earlier. The idea that we need to take care of is that we are dealing with conditional distributions, and as Cooper pointed out, that conditional distributions aren't an easy concept to handle. However, they are very interesting in the sense that they allow us to query things which are involving evaluating different options for the missing things from the distribution or the model, or to sample interesting things if we are given a subset of the observed variables. To do that, we need to minimize a distance metric or some form of objective function from this quantity of interest to the thing that we are approximating. This sort of happens even in the regular neural network domains where we are trying to minimize a loss function. The idea of the loss function is that you have some true values in the supervised setting, that you have some true labels, and you have some parameterized predictions for those two labels, and you want to minimize this loss objective. We're doing something similar to that. It's just that we have distributions this time. So we cannot just say that we have this observed value or we have 10 sets of observed values, but we want to talk about distributions and we want to find another distribution that is closer to the target distribution. To be able to do that, we have to come up with a different sort of loss function, and that is what the scale divergence is supposed to be. So it's giving you a distance between the target function and the function that's your prediction for the target. Once you have that loss function, you want to simplify that loss function so that you can actually evaluate it and optimize that. And that's exactly what's happening over here. We came up with KL, we looked at it. So KL looked like a distance metric. It was sensible to minimize it, but we could not do it because we need to evaluate the target and we do not know how to do that. We found a surrogate, and that surrogate seemed to be useful because it was something that we could evaluate. Once we had that surrogate, we took a closer look at the problem because now we are dealing with distributions. So the way we do the optimization in supervised learning is that we optimize some parameters. We wanted to do the similar thing over here, where we said that the parameters are going to be talking about distribution. And if we optimize over those parameters, that will be similar or same as searching through different distributions. Once we find those parameters, we'll have found a distribution that closely approximates the quantity of interest. I'm hoping that sort of covers it. If it doesn't, we can talk again about it.
I think that was probably better for people. You are allowed, by the way, to just make them unmute and like tell you how they feel about it. I do that sometimes. Just like, all right, ready? Watch this. Everyone unmute. All right, everyone, come on, come on. Oh man, only a couple people did.
I think the explanation is better for me to understand. So I get the gist of the idea. What are you trying to do? But like understand it clearly, I cannot. So I get something out of it. So, yeah.
I think the general idea has landed, but I think some of the finer details are probably a little bit math heavy right now. But yeah.
Yeah, that's really math heavy, so I cannot get the whole thing out at the moment at all.
I think don't feel the need to slow down though. Yeah, can you?
I sort of expected that. The initial idea is sort of math heavy, and it's very hard to give it away with as less as possible. However, as we proceed, we go less math heavy and we go at a higher level. So probably that's going to be easier. But this is sort of the gist of what those concepts are. I do not really know of any way of how to reduce the math heavy component of this. Okay, so I'm going to sort of proceed and hope that I can get people on board with more higher level explanations. Cool. So the idea was to search through family of a distribution and find a distribution that closely approximates the target distribution. Now, we have not talked about how to choose the family. One of the things that people do is that they look at the model that was given to us by the expert and somehow use that to determine which family to choose. The other way is that it's possible that you're not able to even look at the model, like the model that all of us have in our head, which is the model of human face images, or a model that is determined by neural networks. So there's no functional form to it. There is no form to it that says it's defined by Gaussian distributions or beta distributions or gamma distributions. You do not know and you cannot know. So in those cases, how do you choose your Q? Once you even have chosen your Q and there's no issues with that, you still need to calculate this. You still need to optimize your objective, which looks like this, which is an expectation with respect to Q of this function. How do you do this? And do you should you be able to even evaluate this? So this is an expectation, and expectations are sort of hard. They cannot be available in closed form. The only thing that was available to you was the model EZ given X. That's the only function that the expert provided you. It's possible that you do not know how to integrate that function. Or probably a smarter question to ask is, do we even need to evaluate this to optimize it? So this is sort of tricky. We do not need to evaluate the function that we want to optimize. And that's different from the traditional supervised learning. You write that cost function, you use 10 data points, and you evaluate it and you optimize it. However, over here, you do not do that. You do something more tricky. To summarize, we know that a posterior distribution is important, and we need to approximate it. But we understand that VI may be difficult. We'll not be able to evaluate that function, or we do not know how to choose the family. So it's going to be hard to do this. To simplify, we come up with the concept of black box VI, which treats the things as black boxes. So it's partly the reason why I do not want to put pictures to what P, Z, X is going to be, because we are going to treat them as black boxes. Okay, good. So we want to treat them as black box. We do not care what's inside P, Z, X. So I want to treat it as a black box that I cannot look into. I'm just going to use the evaluation log Px, Z, and that's all that I need to talk about variation. That's a simplification, and that domain is known as black box variation inference. Also, the idea is that an expert needs to care only about the model. Whatever they do, that's whatever they have to care about. I am an inference researcher, and I need to care just about inference. So, no matter what PZ given X, BZ, X, the joint distribution you give me, I'll still be able to give you a Q for that without looking into it. And the broader, bigger idea, the main important idea behind black box VI was this. So we had this objective that we wanted to minimize or maximize. And one way to look at this would be this, right? So it's an expectation. So it's the distribution with which this is an expectation, and it's an integral of this function. So that's the standard definition of expectation. Now you want to take a gradient of this. And the core question at this point is whether you can take the gradient and exchange it with the integral sign. So we're going to assume that we can do that. But the problem doesn't end over here. It doesn't end because now we have two functions, and in both of them, phi appears. Because in both of them, phi appears, we have to do something like this, which is a product rule of differentiation. Once you do that and you churn out through the math, I want you guys to believe that this is the only expression that's left over. It's hard to see that, and that's why I do not have it over here, but I want you guys to trust me that it's the correct expression. So we had an initial expression, we simplified it, and this is what we end up with. This looks similar to the template that we saw earlier, a distribution, integral, and a function. So this is essentially another expectation. But the concept of expectation is going to be useful over here, because our gradient for the objective that we wanted to minimize is now an expectation, and we can approximate expectations by taking samples. So if somehow I knew how to take one sample from QZ, the distribution Q, I could approximate this gradient. I do not have to calculate this gradient exactly. I can approximate it. And this is the stochastic gradient descent that we all talk about. So we can do the stochastic gradient descent over here. Once we know how to do this, we can do BBVI. So we somehow choose Q, which is a sensible choice of Q, given the problem. We evaluate our gradient and we update phi. And now we can actually do stuff. How we choose Q is something that's still not clear to us. And we'll not get into this because we can do something smarter, and we'll do something smarter very soon. Somehow you choose Q. You evaluate this gradient that was hard to do earlier. You do this, and then you update your fee and you keep doing your optimization. When you're done with optimization, you will get fee star, which is the outcome of your optimization. Once you have that fee star, you can use the corresponding Q fee star as your approximation for the posterior and do all the things that we talked about. You can evaluate it, you can sample from it, and you can do whatever you want it to do with this approximation. However, as we said, that the choice of family was still going to be somewhat of a problem. And the reason why this will be a problem is somehow over here. So let's say we were talking about the model z given x. This z variable can be a variable that lies between 0 and infinity. So it's just a positive variable. So it only makes sense that you approximate qz with a distribution that has a similar range. It doesn't make sense to approximate it with a Gaussian which has the range over minus infinity infinity. So you want to be smart about it, and you want to approximate it with the right distribution. However, the experts will want to change the model again and again. If you think of the COVID model, experts wanted to change it every time they got some new data or new parameters or information about new outbreaks. So they wanted to change the parameters in the model, and that could very easily manifest in the model changed, the ranges of the distributions changed, and now you want similar things to be reflected in your inference algorithm. To bypass all of this, what we do is that we do a transformation from this constrained domain, which was only positive, to an unconstrained domain. And when you do that, no matter what the problem the expert came up with, you can always transform it to a domain where the ranges are minus infinity to infinity. And another way to say that is unconstrained optimization, something that we do with our deep learning models every day. We do not care about what are the ranges of the parameters that we are optimizing. We just do the optimization because it's unconstrained optimization. Now that we have this, we can always use a Gaussian distribution no matter what the model is. So we get away from that problem of knowing how to select variational family. The other issue was that this gradient that we talked about earlier has very high variance. Think about it. In deep learning, we have the objective, and which was something similar to this, right? The objective was this function. We had n data points, and we just take a gradient of that. So that should be the gradient of this function, not a gradient of something else multiplied with this. What it means is that this gradient estimator is high variance. It's correct, it's not wrong, but it's not going to be close to what it can be or what you want. So this is a very noisy gradient, and we want to use a better gradient estimator. So that's the idea behind automating the choices of black box VI. The two choices were choosing the family and choosing the gradient. We automate that by removing the constraint. So no matter what distribution you give me, I'll always transform it. And once I've transformed it to an unconstrained domain, I can use Gaussians over there without any worry. The other thing was that the gradient estimator was very noisy, and we want to use a better gradient estimator. The way this gradient estimator works is slightly tricky. It's more mathy, so I do not want to get into that. But the essence of this is what we talked about. This is something that you want to optimize, or you want your gradient to be. You have the objective, and you want the gradient to be just next to it. You want to take the gradient of this objective function, the quantity that you actually want to optimize or minimize or maximize. So the reparameterization trick sort of lets you do that. This is the final gradient that comes out of the reparameterization. Instead of z, now we have epsilons, which are a simple fixed distribution. We transform this to become z. So epsilon, some transformation becomes z, so that we have something similar to zi's. But now we can use this form of gradient that we believe was better. And this has proven to be lower variance. it's in general a more default choice now. So the two things that automating the black box VI talk about is that you transform to an unconstrained domain and you just use your Gaussian. So your choice of family is done. You use a better gradient estimator. You update your fee. Whenever you have to use it, you transform back to an unconstrained space, and then you can use your Q free stuff. These transformations, they sound sort of superficial, but they are easier in practice than one might think. And you can always transform back and forth given any constraint domain. So it all works out pretty nicely, and now you can do it the optimization much better. Do we have questions at this point?
Give them a minute to catch their thoughts, I guess. I assume there are questions, but I don't know which would be the best to answer. I guess I'll ask a little bit about reparameterizing and what that looks like if we have we have some how about parameterizing families, because I think that's maybe a little bit of a difficult concept, like how you would go about doing that and what that means conceptually. I know you did talk about it, but
right.
Yeah.
No, I think I very fleetingly went over it. It's just there are a lot of interesting concepts over here, and properly taught in a course, these span over 2 or 3 lectures. So we teach this stuff sort of in graphical models, and in graphical models, this is like a 3-lecture thing. However, the idea of reparameterization is pretty simple. So the core idea, I'll talk about the core idea. It's sort of interesting. It relates to the law of unconscious statistician. It's also known as Lotus, if I'm not missing any word over there. The idea is that to evaluate the expectation of x squared, you do not need the distribution of x squared. You can just work with the distribution of x, right? So if you wanted to evaluate what's the expectation of x squared that we do for or some function of x, you just need the distribution of x. You do not need the distribution of function of x. And that is something that we are doing over here. Our idea was that we remove the dependence of phi over here at the distribution level. The way we do that is that we started with some other distribution epsilon, or for some random variable epsilon. It has a very simple distribution. This can be a very standard distribution like 0 mean Gaussian. So the mean is 0, the variance is 1, and that's just the basic Gaussian, the simplest Gaussian possible. You start with that distribution and you transform the random variable. So you take ax plus b, so a epsilon plus b, that would be one way of doing that transformation. So there is some parameter a, you multiply epsilon with that, and you add b to it. And you do this a epsilon plus b transformation, which will be this t. What you will end up with is a new variable. Now, since you started with a Gaussian, you end up with a Gaussian. And this Gaussian has the mean b and the variance a squared. So this is sort of the known properties of the Gaussian. So this is the way you actually evaluate, sample, and implement Gaussians in all the deep learning libraries or probabilistic libraries that you have. There's only standard Gaussians, and then you do transformation of that standard Gaussian to implement all the other distribution or all the other Gaussians that you are interested in. So that's a very fundamental idea of reparameterization of distributions or change of variable of random variables. So that idea sort of helps us in being able to get to this nice gradient that we wanted. I think that sort of handles it.
Yeah, I think that definitely landed some concepts. That's good. I guess I'll ask, I think, for my own curiosity. So this gradient that we have down here, this approximate gradient, looks an awful lot like the gradient that we said was worse a moment ago, except for this reparameterization. can we guarantee from that I'm so bad at saying that, reparameterization, that we have lowered the variance? Or is there a specific class of reparameterizations that guarantee that?
Right. So, okay, let me rephrase the question. So you're talking about does it? So the gradient that we talked about earlier is sort of more general because um, we can apply it to several places where reparameterization is not possible. So reparameterization can only happen for a Q phi that allows it to be reparameterizable. The Gaussians are reparameterizable. Like you can do the trick that we talked about, that you can do A epsilon plus B, and you will end up with another. However, there can be distributions that are not reparameterizable. So in those cases, you only have the choice of doing this. And that's why I said that you somehow choose Q. Because this Q can be anything, and it can be different, and still this will work out. Because this gradient is still valid. And this gradient sort of appears at a lot of places in reinforcement learning and other places. This is the reinforced gradient and so many things. The score function estimator, score function gradient, and stuff like that. So it's a very general thing that can be used irrespective of what Q is in often places, as long as you can just evaluate this quantity. That's the only quantity that's required. If you can evaluate and differentiate this quantity, you're fine. So it's sort of more general than this one. Because it's more general, it needs to have some issues. And this is like a Q that has to satisfy certain constraints. It's better, but it will satisfy some constraints. So there's always a trade-off.
Thanks. Yeah.
But if you are given a distribution that allows for both, in that case, we say that this is a lower variance gradient, and you should probably use that.
Nice. Thanks. Yeah.
Okay, so now we'll probably get to the more interesting and recent stuff. I don't know how many people will be familiar with this stuff, but the idea was that there is a setup of automatic inference, and there are certain things that you need to care about before you do that, or you need to take care of. There are stochastic gradients involved, there are distributions involved. You need to transform those distributions, and then you will be able to do your optimization the way all of us are sort of used. So, so there have been some other advances in recent VI literature, which are not necessarily VI, but they talk about distributions. And because they talk about distributions, we can assume that they also can be used in variational inference, because variational inference talks about distribution. So one of those things is normalizing flows. And what normalizing flows are is that, in a nutshell, they are the method that you use to define distributions and somehow also use neural networks and very heavy, very expressive neural networks. So to combine those two things, people came up with normalizing flows. So you start, this is very similar to the whole reparameterization story. The idea is still the same. You start with a simple distribution, a simple random variable, epsilon, and you transform it. And you transform it again and again using neural networks. And at the end of the day, you will end up with a very complex distribution. A distribution so complex that it can actually model images. You can generate face images and all sorts of images using normalizing flows. And people have done that using GLOW and various techniques. The idea is that you start with epsilon, and you want to transform it into C. You use some parameterized function. And this function, the parameterization, can actually use neural networks. So this function F can be a neural network. And it's fine. So you send in your epsilon to this neural network and outputs Z, and all of this is somehow going to define a probability distribution. And the way to evaluate that would be use this equation, which is a change of variables equation. So I don't know how people are familiar with this, but it somehow tells you how to evaluate QC. The way to sample it is very simple because this is a simple distribution. You sample an epsilon, you transform it, and you end up with a z. So you sample some noise, some zero mean Gaussian, you transform it using your neural networks, and you end up with the image, with the image of a face image or anything. That's very simple. You can sample from this distribution. How to evaluate it is using this particular equation, where you have the epsilon, you have this function, you evaluate the epsilon in its own distribution, and you evaluate this term. What this term and where it comes from is slightly more tricky, so I sort of skipped it, but we can talk about it if you want to. But this is where the more mathematical part comes in, that this should be fine and this should be doable. So you cannot just use any neural network that you want. You have to be smarter and clever about it so that this term is also easy to evaluate. Once you are able to evaluate this term, you can just tell them that you can do both the things with this distribution. You can sample from it and you can evaluate it. Once you can do that, you can use it for various inputs that people have done. At this point, if there are any questions and people want to know more about normalizing flows, we can talk about that. Otherwise, I'll start. Go ahead. So, apart from the regular elbow, there are other advances that I have talked about. So, elbow was a lower bound for the evidence. That's how we said that it was evidence lower bound. It's not the only lower bound. Neither did we say that it was the best lower bound. So it wasn't the tightest lower bound, and it wasn't the only lower bound. People have come up with different lower bounds, more interesting lower bounds, more tighter lower bounds. And when you have a tighter lower bound, it's supposed to say that if you optimize that, you're going to end up with a better and better approximation. So something that does similar to that is importance weighted elbow. Importance weighting is a very important concept. This is something that appears a lot of places, and it's very, very ubiquitous to a lot of mathematical and statistical fields. What's happening over here is that instead of taking one sample, and so if we set m equal to 1, we sort of end up with the regular elbow expression. So essentially what is changing is that instead of taking one sample, I'm taking m samples. I'm using those m samples such that I'm getting a bound. So in a sense, the math, when it works out, it looks like I'm taking a look at m samples at once and choosing the sample that is the most important among those m samples and doing the optimization using that sample. That is sort of what it comes out when you're doing this importance weighted. And that's a good concept, right? Instead of just taking one step or just taking the next sampling a data point and just using that, what I'm saying is that I'm standing at this point and I'm taking a look at 5 different data points. And instead of selecting them equally, I'm gonna choose the one that's the most important to me. How I decide importance is a different concept, but that's the essence of it. So that seems better, right? If you want to do optimization, you want to take 5 points, you want to choose the one which is giving you the best direction, and you want to take that. So that's what happens with importance weighted elbow. The gradient estimator that we talked about, the reparameterization gradient estimator. We said that this is a better gradient estimator than the old one. However, people have shown that even this gradient estimator can be made better, or this can be improved further, made more lower variance. And the way to do it is again more mathy and tricky. So I'm just gonna put the form. And if you look at this form, it's very, very close, or it's almost the same as the original one. What changes over here is that there is a red colored phi, and what this red colored phi is demonstrating is that this phi is just a copy of your parameters. It's the same value as your parameters, but you will not be differentiating it as a function. You will be treating this as a constant with respect to the differentiating variable. So it will have the same values. it will be used in phase system, but this is a constant with respect to this guy. And if you do that, there are ways to do that, but if you do that, you get a better estimator and it all works fine. Are there any questions at this moment?
I don't actually have a question directly, but I wanted to throw out that what at least I've been told for like TAing is to wait like 2 full minutes to ask for questions, or for them to like ask questions. I'll throw out one, I guess. Is there any sort of easy intuition about why setting those values to constants instead of actually using the parameter would lower the variance? Is there any like intuition?
Right. Yeah, there actually is some interesting intuition to that. So this is known as the path gradient, or I've named it sticking the landing gradient, but it's also known as path gradient. It's a very well-known phenomenon. The above thing is known as total gradient, and this is known as path gradient. In the sense, all it focuses on is that you are using your parameters through this reparameterization, and the only way you want to use your parameters is through the path from epsilon to z. That is the only thing that you care about, and you want to track that, and you want to optimize that process so that you get a better approximation for your distribution. You do not want this recurrence of the fee in the evaluation process, which just masses everything up. So it's sort of easier, a cleaner way, that the only path that I'm interested in is from epsilon to z, and that is the part that I want to emphasize, and I do not want to see this recurrence of phi in the evaluation of q. If I know that, it works out that this is unbiased gradient, so I'm not doing anything mathematically wrong. Everything is fine, and it works out. So that's sort of the intuition of why it should be better. I don't want to track what's happening during evaluation. I only want to track the transformation process, the change of variables process.
All right, yeah.
So now we sort of get to the part that we did for the recent paper. This is gonna be easier in the light of all these things, is that we took a lot of these different components like normalizing flows, importance weighted lower bounds, or different gradient estimators, and we evaluated these in the setup of automatic black box BI. And our idea was that if we use these components in the right way, we're going to end up with the better black box BI algorithm. So we did a lot of things regarding the step size selection, use of normalizing flows, importance weighted training and sampling, the things that we have seen, gradient estimators. Step size selection was like the current method of automatic black box BI has some heuristic way of selecting the step size. So the learning rate that people do with the deep learning, it just selects that learning rate based on some heuristic and just uses that. So instead of that, we came up with something else, and we combined all of these, and we came up with a technique that sort of performs really well. To evaluate it, because this is a black box technique, we wanted to evaluate it on different models. So instead of choosing one or two data sets, we are talking about 30 stand models. So these are 30 different models. And on all those models, the same inference technique works, and it produces better results than anything that's out there right now. So we start with ADVI. We did not talk about what ADVI is, but this is the current baseline, the thing that's most widely used. And we started changing different things to it. So we started adding step size search to it. We started adding our better gradient estimator to it. We started adding importance sampling to it. We started adding flows to it. And we did that in a stepwise manner. Now, since this is happening for 30 models, this is sort of interesting. So when you're doing something that's supposed to improve 30 models, how do you visualize it? And how do you say that, okay, I've had improvements on these many models? And how do you, so let's say you say that I have increased the performance by 1 nats or 1 unit. on 15 models. But you want to see that so the way to visualize this was plotting it something like this, where on the x-axis, what we are doing is that we are plotting the improvement in the lower bound value over the baseline, which is ABVI. On the y-axis, we are plotting the fraction of models that show that improvement. So in this curve, you see that changing the step size to our approach improves the performance by 1 nats or more. That's the unit for lower bounds. So 1 nats or more on 25% of the models or more. So that's one of the ways to visualize the performance of large benchmarks through this complementary serial plot. And if you plotted all these useful components, we had something like this, which was our final approach, which improves the performance by 60% or more models by 1 nats or more. So by using our final method, I'm getting an improvement of 1 nats or more on 60% of the models. And this is 1 nats. Why we're talking about 1 nats is because it's sort of statistically significant. You can see that we are losing performance only on one model. It's gaining the performance on almost all the models. But if you want to see significant gains, this sort of captures all of that. On some of the models, this improvement is 4 nats. And 4 nats is sort of significant if we talk about in log terms. In actual terms, the probability is sort of differing by e to the power 4, which is staggering. So we did that much. That is how much we have improved the lower bound of something. So lessons learned is that if you use our step size, if you use normalizing flows, if you use that importance weight sampling thing, it sort of all of these sort of improve the final performance, and you should sort of be doing all of that. Instead, and this is over full rank Gaussian, which is sort of the go-to thing, and people cannot even do that a lot of times. Things that weren't important was importance with the training and some initialization trick that we used. It's sort of used at a lot of places, but we found that this wasn't consistently useful. So you shouldn't be doing that just because it exists. You should be careful about whether it's actually helping you or not. So there are a lot of studies in the paper that are Bayesian studies and a lot of pairwise studies that validate each of these claims. But this is sort of the summary for the people who want to use this black box VI. Sort of brings me to the end, which is now the transformed story of automatic black box VI. So we had reached to the point that we were transforming to an unconstrained space, but now instead of using Gaussians, we are now using normalizing flows. Instead of using the regular gradient, now we are using the STL gradient, the sticking the landing gradient, or the clever gradient. And then we just update. We transform back to the unconstrained space, and this unconstrained space, now we are going to use the importance weighted sampling. So this is a lot of things, but this is sort of the current state of automatic black box VI. And if you want to do the best of it, this is how you probably do it. This sort of brings us to the end of the slides. If there are any questions, let's take them.
I'll shout out that I felt like I learned a lot. Felt a lot like 688 actually. It was good. Yeah, and feel free all of you guys to ask questions. I know probably a lot of the math stuff didn't 100% make sense. Some of them are like freshman stuff, but I think overarching concepts, you still probably have a lot of good questions to ask. So I'd say go for it if you feel like you have a question.
It's possible that a lot of this is mathy stuff, and also even those who have done probabilistic models, this is sort of the last thing that we cover in variational inference. And this is one of those things that like sort of your coursework ends and research begins. So it's something that people often are not familiar with, but we can talk about even the more basic stuff than that if any of you are beginners and want to know how to go about any of this.
I'm guessing that people feel a little bit intimidated by it, but also I'm sure they all picked stuff up and like learned something there. So if anyone does have a question, I'd go for it. There are lots of good questions to ask here.
Hi. So I just got out of the class and I joined a bit late, so I was kind of didn't really catch the introduction to what the research was 100% about. If you could just recap briefly on that, please.
Oh, sure. I'll have to go a bit further up. Right. So the research is about right. So the problem is that an expert decides a model, and there are two components to the model. They're going to be something that's going to be observed and something that's going to be hidden. So think of the model as the model of human face images. Like you as a human are expert at that. Given a human face image, you can evaluate it that yes, it is actually a human face image. Or given even a part of it as to observe, you have some sort of a model in your head that tells you that option A is sort of less likely than option B for the hidden part. Right? So if you were to ask a mathematician, they will say that you sort of used this distribution PZ given X, which lets you evaluate option A in this distribution and tells you that this value is lower than when you evaluate option B. So option B is more likely in this distribution than option A. And this distribution is known as the posterior for the model that was given to you. And this is always the quantity of interest in any probabilistic modeling problem. And then we talk about how this quantity of interest is hard to evaluate. But if you were able to evaluate and sample from it, this is probably how you would be useful in. Then you would want to evaluate options given to you, and you would say that when I evaluated in that quantity, it was less likely or more likely. Or if you could sample from it, you would sample and you will get a latent part or the hidden part that looks something like this when you were only given the option. So that's why it's a quantity of interest. You want to evaluate it and you want to sample it. And what we discussed in entire slides was the way to do that was variational inference. It's a lot of mathy stuff that we very with a lot of effort we got through. So I'll not get into that, but that was the initial broad idea of this problem set.
Thank you.
Hi. Thanks for coming down, Abhinav. I have a question. So, what did people use before VI to approximate the intractable?
Right. Yeah, that's a really good question. So what I missed or skipped over here is another method to approximate VI, and that method is known as NCMC, which is Markov chain Monte Carlo, which is even more mathy. But the idea of that is that you do not need to find a parameterized field like we did in variational inference. You do not need the subjective or stuff like that, but it's some way of sampling and from the posterior. And once you have the samples from the posterior, you just need the samples to do anything that you wanted to do with the posterior. Why? So the posterior, so we are, I think, I'm going to assume that we are sort of sold on the idea that posterior is important. Another idea that I want you to take away from this talk is that probabilistic models means that you will be interested in posterior. And if you're doing probabilistic modeling, it means that you will be taking expectations with respect to posterior. So once you have that posterior distribution, the way to use it would be taking expectations with that distribution. And the good thing about expectations is that you can approximate them by just the samples. So if you had the samples from that posterior distribution, you can forget about whether you could evaluate or do things with that. So if you just had the collection of that sample, so if I gave you 1,000,000 samples from the true posterior, you will be fine. So MCMC is a method that gives you that collection of samples that are, if you give it enough computation, are sort of guaranteed to come from the true posterior. So it gives you a guarantee that you can get samples from the actual posterior, but it's just going to be very, very hard to achieve that.
Oh, okay, so does this achieve a trade-off between the guarantee and the computational? Like how it is more computational?
Right.
Okay, got it. Thanks.
Right. So there's a trade-off of how much computation you are willing to throw at it, and how accurate those samples will be. So it's about running a chain. It's Markov chain Monte Carlo. It's running a chain. The chain starts at some random data point, and then it transforms it into the sample from the true distribution, right? Now, if you stop the chain in the middle, it has not reached its actual destination. So it's going to be closer, depending upon how close you stop that chain, the better your approximation will be. So if you stop it much sooner, it's going to be worse. If you stop it when it's near to the destination, it's going to be fine. So it's sort of that trade-off.
Got it.
All right. Well, I actually have a class coming up, so I assume some other people do too. So yeah.
Yeah, if I don't know whether people want to look at this stuff or not, I can share the slides if they want to. Like you can ask me questions later on also.
Yeah, no, absolutely. And if anyone, if you can check here, I'm sure people will maybe post some stuff here about it, perhaps. And I can direct any questions to you too if anyone wants to just ask me them, and I can link you up. Yeah, I appreciate it a lot for you coming. Yeah, it was good. It was a lot of information. It was good information. I certainly learned a lot, and I'm happy you came. All right.
Okay.
Yeah, I also I did record it. If you want a copy of it, I can send it to you. I'm